Coming to the second session, which is based on digital design simulation, which would be delivered by Engineer Uday from SCL Mohali. For this, I would like to introduce him firstly. Engineer Uday has completed his BTech from Walchand Institute of Technology in 1999. After that, he did his PG diploma in VLSI design in 2001 from University of Pune. He is serving the Semiconductor Lab Mohali from 2001. He is involved in the design and development of digital mixed signal ASICs from RTL to GDSII in formats. He has also developed digital ASICs for launch vehicles, camera, electronics, timing sequencers for CCD devices. He also designed the digital controllers for video signal processors. He developed standard cell library, or you can say process design kit for different technology nodes. He also created in-house development of standard cell library characterization EDA tools, developed IBIS IO models, then further development of foundry specific ASIC design methodology at each node and addition of different flavors as per the project need. And he is working with 32-bit and 64-bit microprocessors, and he is also providing PDKs, EDKs support for ISRO, DRDO, DAE, SMDP industries under DIPP. Why? His areas of interest are digital ASIC design, low power design, PDK development, standard cell library. With the long list of his achievements and glory, I would like to invite him. Sir, please put light on the topic of digital design simulation. Sir.
Okay. Thank you, madam, for the kind introduction. So, as the content of the course is digital design simulation, so I would like, before going to direct simulation, first we will discuss what is the digital design and what are the what do you mean by design, how you can implement this design, and for that implementation there should be certain methodology which you should follow so that you will get the proper functionality and proper performance after first silicon. Our goal is not to just do simulation and do check functionality. Our aim is to use this chip in some particular mission. So our target should be we should do digital design simulation. But before starting any simulation, we should focus first on the what is digital design and how we should implement and how we should perform the simulation. So before starting any digital simulation, we should first discuss what is digital design. So as you are already aware of Moore's law, there should be change in the technology after 18 years with respect to complexity, with respect to technology, with respect to methodology. So at each particular node, you should follow the methodology provided by your foundry. So at each node, there is a specific sign of, or we call that may be timing closure, power closure, SI closure. So according to technology node and according to your foundry specific requirement, you should follow the design methodology. So before starting any methodology, we should first discuss about the what is the design. So before starting any design, you should aware of why there is need of any design. So design, suppose I want to make some microprocessor. What is the requirement? Suppose I want to use in some mobile phone or in washing machine or in some launch vehicle, in some camera. So I should know what is its application, what is its requirement, what is its time to market. So according to I will start my methodology. How I should start from? So first specifications for particular ASIC, they should be known to a designer. So designer should can do simulation or any VHDL coding, RTL coding, placement and routing according to its application. But before starting any ASIC, he should be aware of what is its goal. So this goal can be implemented through different methods. So suppose he want to make within 2 months, within 3 years or 1 year, or what is its goal? It has to just provide some ASIC or make some mobile camera, and that should be launched before suppose Diwali. So in that case, suppose only 6 months is available in his hand, he should start with the prototyping in FPGA and provide all the ecosystem required for my particular mobile phone, so that he should develop his RTL code, dump in the FPGA, and provide all the ecosystem required for its camera, its Android application, so that once his chip is ready, all the complete ecosystem should be ready. So for that purpose, he should know what is its requirement and what are the specifications. So design can be implemented in various ways. So we'll start with the implementation way. We will discuss what are the different methodologies useful for any ASIC design. So before starting any ASIC design, we will discuss what is ASIC. So ASIC is an application specific ASIC. There are various kind of ASIC. That may be standard product, that may be application specific standard product like microcontroller. That is ASIC, but that should be specialized for particular industrial application, that is specific for particular any commercial application. So according to requirement, the application specific standard product or application specific ASIC is designed. Application specific IC is not only a memory or not only a single analog block. It may be analog, digital, memory, or SoC, which contains all these all kind of designs. So it may be, suppose timing sequence. Suppose I have made one charge coupled device. So suppose this is complete analog device, but for using that charge coupled device, I require some control logic which should be in digital format. For powering that device, I require some LDO, power management kit, which can provide supply to this chip. So according to my application, so I will specify the specification for my chip. So suppose in this, suppose we will take system which contains CCD. So for that require one CCD chip, one digital chip which can provide different clocks required for CCD operation. So for that, my goal is to generate one timing sequencer which can provide different different kind of clocks. So according to my application, I will switch to application specific ASIC or FPGA or any system layer board. So according to whether it is imager chip or any RISC processor, I have to start the design of my ASIC. So why ASICs are required? So it will depend on the type of application. Suppose we require 8051 microcontroller for industrial application. We require so this is general application. We required in huge number. So the microcontroller cannot be made in FPGA. For this kind of application, we should go to ASIC. Then we require for space application or military application, we require specific ASIC which cannot be standardized for common people. So in that case, we don't require any volume, but we require reliable and high performance devices. So in this case, we will go for ASIC, which are required for particular space application or military application. So according to requirement, we should go to different kind of methodology. So in case of ASIC, there are different methodology. So all the designs are actually ASIC. That may be full custom ASIC, standard cell ASIC, gate array ASIC, or FPGA. Most of you students, you are using FPGA for your prototyping at your institute. Full custom ASIC. In case of full custom ASIC, we will start from scratch. So we will, suppose we want to make one inverter, we can directly put individual devices, NMOS, PMOS, and draw each polygon at transistor level and start with its topology, and we will characterize each, calculate the sizes of each MOS and make a block, and then we can integrate all this block in full custom method. So in full custom method, we have to draw each polygon at transistor level. Then all the analog circuits are made in this way. Or in case of, suppose we are making some microprocessor, and in that case, suppose we are not meeting our timing. So in that case, we have to optimize the particular block. Like suppose we are creating FPU, and particular our floating point unit, particular block is not we are not able to meet timing. So in that case, we want to switch our digital methodology to full custom methodology. Or in case of clock tree synthesis for particular processor, if we are not able to meet this timing with the digital methodology, in that case we have to make all this clock tree in full custom way, so that we can meet all the skews and all the timing parameter of the processor. So in case of full custom ASIC, all the masks are required. Suppose we are using 4 metal, 5 metal, 6 metal. In that case, we require around 24 masks to 30 masks according to our requirement. So this is the one example of full custom ASIC. Here is one example of OAI gate. In this case, we have made around 30 MOS. In this case, all the MOSes are made manually. All the layout and all the number of contacts and vias are drawn manually with the help of P cells. So it is time consuming, but here performance is better. So all the analog blocks are made in this fashion, and digital standard cell library also made in full custom method. So next part is standard cell ASIC. So we'll just go through this standard cell this part, and then we go to design and simulation part. So standard cell ASIC is everyone is aware of. You are doing VHDL coding, RTL coding, Verilog coding. So next step is the synthesis and place and route. So for standard cell synthesis and placement and routing, the core part is standard cell library. So what do you mean by standard cell library? So standard cell library is a all the cells are like basic building blocks, inverter, NAND gate, adder, multiplier are made in a full custom method. All they are characterized for particular process, voltage and temperature, all the environment, and all the characterized data for timing, model and noises is kept in a particular synthesis liberty format, and all the cells are particular load, particular slew is available in standard cell library. Suppose we have 500 cells in our library, we have to characterize all the cells in all the process corner. Then we have to make all the timing and power model for all the standard cells, and all the cells are layout should be available. Then all the layout view, then placement and routing view, then abstract view, all the abstract view in left format or Milky Way format, that should be available for standard cell library. So in this case, what is the standard? So standard is the all the I will show an example. So this is one of the example of this standard cell ASIC. So in this case, all this it is seen that all the cells are placed in on particular row. It is you can observe the height of each row is constant. So in this case, all the cells are placed in one particular fashion, and the height of this particular all the cells is constant. Height of power and VDD and ground is common. Then it is found that like if you have 4 metal, then metal 1 and metal 3 routing is horizontal, and metal 1 and metal 2, metal 4. All this blue in color, all these are metal 2, and it is routed in one common format, that is in vertical routing. So this is standard which we are defining standard cell library. So metal 1, metal 3 is routing in horizontal, metal 2 and metal 4 routed in vertical fashion. So all these standards are defined in the standard cell library. If we route metal 1 in vertical and metal 3 in horizontal, then there may be congestion, and we cannot route in particular assigned area. So then there is height is fixed. Then each cell is driven by half DRC. So all the standards specific to placement and routing and timing and power are followed in standard cell ASIC. So in standard cell, all the standards are provided by foundry. Like all the cells are characterized for particular. Suppose we are using library at 200 megahertz. So in that case, what is the standard for timing? Suppose in that case, all the cells are characterized as suppose 200 megahertz, then its time is 5 nanosecond. So thumb rule is rise time plus fall time should be suppose 10% of the my highest frequency. So in that case, it is all the standard cells are characterized for the 10% of the my maximum clock. So all the cells are characterized in this respect. So all the standard cells characterized in particular standard, they are available and provided by the foundry. So in this case, foundry will provide all the standard cells, and designers or RTL that means a designer just use this characterized library. Wow. So what is the advantage of this standard cell ASIC based approach? Here all the cells are available. We have to just pick and place and do synthesis and place and route. So within few weeks we will get our synthesis netlist, and within few weeks we can get placement and routing, and within 3 months or 4 months we will get our complete ASIC. So here also we will get we require all the number of mass, and but it is very completed within a very short duration. So this is the advantage of standard cell ASIC. Full custom ASIC require time consuming but performance better. Then intermediate option is gate array ASIC. So for low volume and low performance ASIC, we can use the gate array ASIC, which is not used nowadays. But some particular application or some lower performance like 10 megahertz, 20 megahertz, and some lower quantity, we can go for gate array ASIC. Here only we require only metal mass. All the standard cells are already placed in the place on the device, and we have to just route and use only metal mass for the only metallization mass are required. This is low cost, low performance. Is used for low cost, low performance, and low volume option. Then the FPGA is used normally used for the low volume or some prototyping or here everything is all the cells are pre-characterized and silicon available on silicon. We have to just make one bit file and just dump. So for rapid prototyping or development, suppose we are developing processor. So in that case, we have to develop our ecosystem. So in that case, FPGA is useful for developing a prototyping. So while developing ASIC, we can develop complete ecosystem. We can develop compiler or all the memory interface with the help of FPGA. We will finalize our VHDL code or RTL code and dump in FPGA and start developing our other ecosystem. So this is for low volume. It is available. So although it is available with all respect, with respect to yield, with respect to DFT, with respect to performance, but it is more power consumption more in case of FPGA as compared to ASIC. So according to your application, you can first you have to finalize your specification, and according to specification, you should go for which type of methodology you should follow. So before starting any ASIC, you should consider how to choose the methodology. What is your time to market? What is your number of devices? What is your applications? Suppose we require processor 1 gigahertz processor, which is readily available in the market, but that is not that is not suit our requirement of space requirement. So suppose we require 100 kilowatt this radiation requirement, but commercial processor are not capable of performing this radiation hardened environment. So in that case, we have to proceed with the ASIC, which can ASIC with the help of radiation hardened library. So time to market, then the requirement, and what is the use of end application that will decide your methodology. Then you should also, before starting any design, you should be aware of what is its cost, what is the how many parts are required, what is the NRE cost, what is the cost of your synthesis tool, layout tool. Suppose we want to develop an ASIC with the help of 10 engineers. So what kind of EDA and CAD support is required, what kind of foundry support is required, what kind of post fabrication facility like packaging, then we require automatic tester. So all this cost you should calculate. Suppose that means suppose time is only 2 months, design time is 2 months, your all the tools are available, but for that package is not available. Design is running in simulation, but you don't have any facility for debugging, or you don't have a tester facility, you don't have any package facility, then there is no use of dies are available. But if you don't have any debug facility or any testing facility or any system facility, so only simulation is only like your game only, like your game on a computer. So your goal is not to make only perform simulation. Your goal is to make chip that should be work and that should be used in the system. So according to your application, according to your requirement, you should check your design methodology. So you should survey before starting any device. You should calculate your cost, how many number of masks are required, and what is the your goal per. Then before starting any design, you should one is cost, another is technical feasibility. Suppose I want to design suppose 500 megahertz processor. So you should select such a process which can take care of this 500 megahertz processor. Suppose at present we have 180 nanometer process at SCL fab. So whether that is sufficient for 500 megahertz, or I should go to 130 nanometer or 180 or 90 nanometer. Suppose the 90 nanometer provide 500 megahertz support, but the cost of that mask set at 90 nanometer is suppose $500K. So that is not suit my this cost factor. So in that case, I want to switch to 130 nanometer or 180 nanometer and take the do the feasibility. So before starting, the process and all the things is available for simulation. You should decide whether that is that means commercially feasible. Then suppose at 180 all the flavors are available, so 3.3 volt, 1.8 volt, 5 volt. So you should at particular process selection and flavor selection is very important part of your start before starting any project. So you should aware of what is your power budget, what is your timing budget, what are the IPs are available. Suppose you're developing your SoC and all the memories are available at suppose 1.8 volt and you are working on 3.3 volt. So whether that's sufficient lever translators are available, sufficient IO pads are available. So you should do all the feasibility before starting any project. Your goal is not to do only simulation. Simulation is just aid to check your functionality, whether all the performance is met or not. You should take care of all the that means pre and post. What is the end use of application? Whether RTL coding is not, you are not any programmer. You want to design, your design should be with respect to how your design can be tested. Simulation is not your just goal. Your goal is to test that chip after fabrication. So you should aware of what kind of package is available, what kind of DFT techniques you should use for the testing at the system level. So you should aware of what are the requirement of all the ASICs. What is its complexity? What is its silicon efficiency? If you are going to make one SoC, but whose size will be going on. Suppose foundry can make 20 by 20 mm chip, and suppose your chip size is going to 18 by 18 mm, 15 by 15 mm. So whether suppose you are going to make one memory like 16 MB memory, and whose size is going to 15 by 15 mm. So what is its silicon efficiency? Suppose yield is 10 to 20%. There should you should take different approach. So you should aware of all the characteristics of your PDK, your foundry kit. All the you should aware of all the characteristics. So before starting any design, you should aware of all the what are the trade-off of the designs. So you are not any computer programmer, you are not building any website, you are not building, you are doing VHDL coding, but that should your aim should be to target particular technology and particular hardware. So as I mentioned, the foundry will provide the standard cell library which contains all logic gates, all the standard cells, inverter, NAND gate, adder, multiplier, multiplexer, decoder. Foundry will generate generic standard cell library, but the designer should select. Suppose Foundry had made 1,000 cell, but if there is no requirement of 1,000 cell, you should select your particular standard cell library from the available cells. So you should use proper use of buffer. So Foundry will provide different kind of buffers. Like there may be balance buffer, there may be some non-balance buffer, there may be some clock delay buffer, there may be some clock tree buffers. So according to your application, you should use the proper use of buffers. Then in case of selection, suppose then after this we will discuss the core and mega cells, some limitation of synthesis tool, IO cell, ESD cells, design for speed, then design for why we are designing. It should be clear from start, whether it design for speed, design for reliability, design for testing, design for manufacturability. So you should aware of the what is your goal, and then you should target particular design methodology. Suppose you are going for the design for reliability. Suppose it should be used in the space. Then for with respect to design for reliability, you should use different approaches like triple mode redundancy, or you can use the different architecture which can take care of the reliability aspect for the particular mission. So your goal should be clear before starting any design. So we will discuss this in next slides. So selection of cells, as I mentioned, there are a number of cells are available in your standard cell library. Suppose there are NAND gate available, NOR gate cells are available, but you should that is customize your synthesis or placement and routing according to your requirement. Suppose there are 2 input NAND gate, 3 input NAND gate, 8 input NAND gate, 16 input NAND gate. So suppose according to your functionality, 8 input NAND gates when meets your timing. So in synthesis, that meet your timing, but after post layout or placement and routing and post layout, it your timing is not met. So what is the problem? You suppose you have selected NAND gate with 8 inputs. So it will your timing after RTL will do synthesis, and after synthesis it will meet your all the timings. So you will be happy. I met my all timing at 100 megahertz, but after post layout it is coming only up to 75 megahertz. Then what is the problem? In that case, suppose you have 8 input NAND gate. So in that case, 8 input NAND gate size is bigger. So layout size is bigger. So it will occupy more area. And with due to that, what will happen? There are very less routing tracks available for the routing for the NAND gate. So it will occupy. That means it will meet timing requirement in synthesis. But after routing, there is congestion due to that bigger size and very less tracks are available. Instead of 8 input NAND gate, if you go for 2 input and 4 NAND input, so you can that means place that smaller NAND gates in different location, and you have different routing tracks, so that there will be less congestion. So according to your requirement of or your budget for timing and power, you can select the standard cell. So particular suppose you are getting any this kind of violation, then you can restrict your standard cell library. Don't use higher fan out, 8 input, 16 input fan out. You should avoid. So you should use optimum fan in fan out for your requirement. Suppose you are having different fan out cells like 2 input, 4 input, 8 out. Sorry, fan out is 2, 4, 8, 16, 32, 64. In that case, suppose you have done synthesis, and it will suppose you have 64 x fan out, and it will drive all the for your particular timing. It will drive. Suppose your load is 35x, and 64x buffer can drive 35x load. But in that case, there is a due to routing limitation, there is a due to routing, the synthesis tool will select the particular highest fan out buffer. But in that case, due to the highest fan out buffer, the power consumption is also more. So if you restrict, maximum fan out should be 32, and you will route the routing should be such that this load of the interconnect is less than 32x. So if you constrain your synthesis tool, routing my maximum load is 32x. So synthesis tool will insert buffer at regular interval, so that the interconnect width interconnect length is not more than 32x. So you have to optimize your fan out at the time of synthesis. Those synthesis cells are available to drive 100x, 60x, 80x, but you should restrict your synthesis tool so that it you can set constraint in such a way that interconnect load should not be more than 32x. So your goal should be not only VHDL programming. Your goal should be toward how to meet timing, how to meet power. So in that case, those standard cells are available. You have to restrict your synthesis tool through proper use of constraint. So proper use of buffers. In case of clock tree synthesis, our aim of clock tree synthesis is to minimize the skew. So in that case, you have to mention to use the only balanced buffer, so that the skew is skew is equal for rising and falling path. So you should take care of the how to select cell according to your application. So buffer design is also part of this same, whether how to select number of chains, number of whether it is power you require for delay buffer or for specific to power. So according to you can design your buffer. This power and delay trade-off should be there. So whatever you design, that should meet all the speed requirement, and it should not take much time for design. So at the time of RTL, you should also take care how to increase my simulation time. So you use process or always statement, which improves your simulation time. Minimize the number of signal in the sensitivity list. If there are large number of signal in your sensitivity list, it will at each for each signal it will activate, deactivate, or it will simulation time will be more. Similarly, do not model small process, because too much small process will increase your simulation time. Do not use block statement. because block will be always on, and that will also increase simulation time. Convert vector data types, that will also reduce simulation time. So you should write RTL taking into hardware and your simulation time. So you should take care at each level the different guidelines for your particular process. Suppose you are doing topological synthesis. Some normally at lower frequency or older technology we are doing wire load based model synthesis. In wire load based model synthesis, we are estimating some according to fan out. It will calculate R and C for particular load or particular 1K, 2K, 5K gate count. We will assign some wire load model, but that will increase my synthesis to layout and then synthesis layout iteration. So for that we will use topological synthesis. So this will improve my speed is increased and with less iteration. Then what are the post layout interconnect information that is available at the time of synthesis only with the help of topological synthesis. So this is all the interconnect issue after post layout, they are resolved through topological synthesis. Then according to your timing requirement, you should use multi-VT synthesis, low VT, high VT. So Foundry will provide multiple libraries for multi-VT requirement. So you should use the multi-VT synthesis. Then SDC constraints should be proper, though, because all the you should aware of the GIGO, garbage input, garbage output. So synthesis tool will do according to your constraint. So whatever the constraint you will provide, your synthesis tool will change your RTL to synthesis. So whatever the SDC constraint you are providing to your synthesis tool, that should be proper. Suppose you are for interconnect, suppose you are given set max load less than 30, max load 32x. So it will insert buffer at particular interval so that there will not be any high fan out buffers. So this kind of constraint you should provide at the time of synthesis. Then all the timing constraint all that are must, but for speed improvement you should provide proper SDC constraint. Then before starting your design with respect to synthesis or with respect to layout, you should have the floor plan. What is your suppose you are developing some microprocessor, you should aware of all the peripheral and all the memory and all the position of analog block, digital block. Suppose you are making one SoC which contains some LDO, one some LVDS receiver transmitter and some ADC DSC. So all the position of each block should be known before starting any layout. So you should take care of all the design requirement, like what is IO load requirement. So in simulation, you if a chip will work, but after simulation, if you know if you are not chosen your IO cell properly, there may be discrepancies that will work at 1 megahertz, at 10 megahertz, but at 50 megahertz or 100 megahertz it will not work because you have not taken properly package parasitics or post layout data. Like you're not you have taken all the done synthesis simulation, post layout simulation, but you have not taken package RLC or the traces of the your PCB or all the IO loads, external loads available to chip. So in simulation it will work, but after post layout, due to non-availability of package RLC, chip may fail because there may be some IO drop or there may be some overloading due to external peripheral. So for that you should know your all the environment, what is package RLC, what is PCB RLC, what is your environment, what are the load, whether it's resistive or capacitive, so that you should select proper IO cells. Sometimes selection of IO cell, if you over constrain, then there may be issue of it will there may be that means there will be more leakage current. Though suppose your requirement only is only to drive 1 milliampere and you have chosen 16 milliampere IO pad cells. So in that case, there may be over constraint. You should know all the so for 1 milliampere IO load, you should select pad which can drive 2 milliampere. Though 16 milliampere IO pad is available, there may be over constraint on your design. So according to your requirement and according to your design, you should go for your proper selection of IO cells. Then next goal is you have to make design that will work functionally, but electrically it's okay, but due to environment or due to its at after particular some life, their problem of reliability may get started. So you have made design that will work on simulation. After fabrication, it will work, but after suppose 30 day, there may have chances of failure, or at 125-degree, there are chances of failure. So you should design your design in such way that it will meet all your requirement. Suppose for a space specific requirement, we require -55 to 125 at. Okay, again we can recap and start this design for reliability. So as we discussed synchronous asynchronous design, use of transmission gate, you should check uh, some spice simulation also for latch up kind of thing if you are using transmission gate. In case of IO pads and power pad, you should be aware of the what is the requirement of environment and how much power pad you use for particular application. Otherwise, there may be eye drop inside your chip. Then you should take proper metal width for your particular application. Then for with respect to reliability, you should use sparing, that may be hot sparing or cold sparing according to your application. And one of the most important thing, if you're using multiple VDD or multi-VT or multiple VDD options, or if you are using any LDO or level converters, power sequence, you should be aware of the power sequencing, and all this should be properly checked for with respect to reliability. Otherwise, there may be huge current flow in case of if you are not follow power sequencing options. So your design should be such that it will make not only functional or electrical performance, it should meet all your reliability criteria. The next is design. Another aspect for design that should be testable. So you have done all your design, your for different block A, block B, block C, block D. But if it is not working after fabrication, so there should be for the there should be provision for testing at each stage. So uh, you, you should follow design for testing with the help of scan insertion, or with the help of your beast, or with the help of boundary scan. So normally, if you're using VHDL or RTL based methodology, you should use scan based methodology. You should use DFT, and the fault coverage should be more than 95%, so that your each node should be tested after fabrication. So that should be done with the help of your synthesis tool, with the insertion of scan flip flop instead of your normal flip flops. You should also involve boundary scan, BIST or JTAG according to your requirement. So all the blocks should be testable after fabrication. Only that should not be work at simulation, but that should be tested after fabrication. So this is the need for design for testing. Then design for manufacturability. Then if your design is working at simulation, if design is working after fabrication, but you should have for high volume or high performance your circuit, there should be particular 90 more than 80%, 90% yield. So for if circuit is working, but the yield is very less, like in case of memory or in case of imager or any big size SOC, your goal is to that should be functional, electrically okay, reliable, but that should also perform yield analysis. So with that respect, you have to follow particular spacing rules. You should insert redundant vias or metal split with respect to stress analysis. You should follow antenna rules and metal rules. So suppose you are using 90 nanometer and your minimum spacing between uh, two metal wire is suppose is 100 nanometer. So but your memory yield is coming only to 25%. So in that case, you have to increase instead of 100, as you are already shrinking your technology. Instead of 100, you can use 105 or 1010. So you should take your own margin, and for critical nets, you can increase the spacing so that there should not be any open or short, and you will get better yield. So with respect to OPC, with respect to your RET, or with respect to it, you should increase spacing according to your fab requirement. Then there may be a problem of the particular via opening. In that case, it's recommended you should use multiple vias instead of single via, because if single via is not open, your there may be open in a circuit. You should follow the slit at suppose you are using your current requirement is suppose 10 milliampere and your current density is 0.5 milliampere per micron. So in that case, suppose your metal width requirement is suppose 20 milliampere, and there are chances of stresses on the particular metal. So in that case, if there is foundry will provide some slit rules, like for normal metal spacing is suppose 0.1 micron. For fat metal with more than 20 micron, it should be 0.2 micron, and it should insert metal slit in case of fat metals. So you should follow all the design rules specified by foundry with respect to slit, with respect to antenna, or with respect to dummy metal field. So with respect to design for manufacturability, you should follow all the rules provided by the foundry. For metal field, which is required for CMP purpose, antenna is required for your post post manufacturing this antenna purpose, and metal field for this test purpose. So you should follow all the manufacturing rules. So ASIC design is very complex. So you should follow rules and regulation at each node. Suppose you are starting at RTL, you should follow all the rules. Then you at syntax, you should follow the methodology, or what is the topological methodology, or all the ST sequence. At each stage you should follow, and you should be disciplined it at this stage, because single failure at any single stage there will your chip. So no single step is should be no single step is all that complicated, but there are numerous number of steps of involved. So many of the steps are repeated. Like suppose you are doing simulation for one PVT corner, and like there are like slow, fast, typical. Then there are voltage, voltage and temperature variation. Suppose for all that we require, for one single circuit we require simulation and 45 corners. So for that it is manually that means doing simulation and checking all the simulation at each process corner is very tedious job. So in that case we should go for any scripting. So for the scripting we should go through some political or skill, any scripting language is required. So only VHDL coding on only simulation is not sufficient. So for all the PVT corner you should perform all this simulation through with the help of scripting. So so that there should not be any slippage of any functionality. You should aware of all the setup provided by your EDA tools, like CDS.ly for in case of cadence, DC setup for synopsis, and all automation should be done with the help of your scripting, so that there should not be any missing link. What are the benefits of scripting? Because suppose you want to do one standard cell library, suppose I want to make flip-flop, and in that case flip-flop I have to make like all the timing analysis, all the setup time, hold time, recovery time, remote time, all the TPLH, TPHL, all its data. And for single flip-flop I require minimum 500 times of spice simulation. So in that case multiple corner, multiple load, multiple rise time, fall time. So in that case I require multiple spice simulation, but only with the spice simulation I cannot do complete cell library correction. For that I want to make rigorous scripting and automate all the cell library characterization, then characterize the data and format into particular synthesis.lib format. So in that case without help of any Perl or Tcl script, it is not manageable to perform spice simulation, because spice, you are expert in spice simulation, but managing all this huge data is very tedious job. So in that case you require scripting for any Perl or Tcl script. So the design process for transform your code to silicon in steps. At each step, design is checked against a known correct reference, and this reference is known as golden reference. So you should follow all the golden reference which provided by your design house, your EDA house, or your foundry. So if you are following all these golden reference, there are chances of you will get first time success for all your designs. So for first time success on silicon, you require need for discipline. What are the rules at each stage, at RTL, at synthesis and placement and routing, and at post layout? You should follow all the rules provided by your design house. Then you at particular node, at particular technology, you should follow all the sign off criteria provided by your foundry. Like for 180 nanometer, we require timing sign off. Suppose we go to 130 nanometer, we require timing plus power sign off. At 90 nanometer and below, we require timing sign off, then OPC sign off, RET sign off, then litho friendly design. All these different kind of technology specific sign off required, we should follow, so that there are chances of first time success. So this is our typical EDA flow which you are using for all the design at SCL. So this is suppose we start from RTL. Then next step is synthesis. Before going to synthesis, we'll check the quality of the RTL, that is through with the help of LEDA. So I will discuss this all these steps in next slide. So RTL, then synthesis, then DFT or scan insertion. Then we'll check the formal equivalence of this RTL versus the scan inserted netlist. Then we'll do pre-layout simulation. Then there should be review of the specification, then placement, then floor plan followed by placement, routing, clock synthesis, then physical verification, then again formal verification of RTL versus post load netlist, and then final timing sign off, then back conversion of the HDF file, then DFT and ATPG analysis, then final again critical review for the specification. So this is a typical flow which we are following. So I will discuss all these steps in next slides. So this EDA flow, we should follow all the steps. So first step is, once RTL code is ready, your goal is not to just define your VHDL coding. You are not a software programmer. Your aim is to your goal is to perform simulation that is only for functional checking. Your goal is to generate hardware which is timing with respect to timing, with respect to power. So for your goal is to write VHDL code in such a way that you will get the optimize the hardware. So for once you started your specifications are final, and if you are going to writing VHDL code, so that VHDL code should follow all the syntax and the design rules provided by your foundry. So that should be you cannot check manually all the syntax manually, or the all the coding goal provided by foundry. For that you should use linting checks, that with the help of LEDA. Suppose you have written code, but that is not synthesizable. So, and suppose you have provided VHDL code and provide your VHDL code to your foundry for synthesis and post layout activity. But that if that code is not synthesizable, there should not be use of that code. So in that case, your VHDL code that should be lint free, and that should be checked with the help of LEDA or any formal equal or any linting tech. Suppose you have written any VHDL code that is not meeting your foundry requirement. So suppose reading from an output. So we are getting this linting error, reading from an output. So this is not synthesizable, or this is synthesizable, but when the value of output is also used internally, it is recommended to add a buffer. So in linting check, this will take care of your VHDL code. So your aim is not to just make VHDL code and check the functionality. With the reading from output port will clear your functionality. But with respect to reliability, it will there may be loading of that output port, and it is the same signal is going internally. So in case of linting check, linting check will check the quality of your VHDL code or Verilog code. So before starting your simulation, you should pass through your quality of linting check, quality of your VHDL code, whether that is synthesizable, whether it will meet all the clock getting requirement, whether it will meet your all generated clock reset, on all the quality of the VHDL code that should be checked through help of linting tools. So linting tool will check all the quality of your check. It will check whether any, if you use any component or any IP, that should be that whether that library or complete IP is available. If you are use any FSM and all the states are not use, or if you use any case statement and others is missing, so in that case any default conditions are available in case or any FSM, that should be checked in lint check. So your first after writing any VHDL code, your first aim to use your RTL should be lint free. So you will get all the reports in your linting tool, like LEDA. Like suppose you are using the this WD equal to 0, flip flop with tied input value is detected. So this report is available in your linting output. So you have to check whether it is intentionally made 0, or if there is any some typing or any mistake. So you should check whether linting shell will warn you. This is the warning. So you have to decide whether it is warning or it is intention of your application. Then so this LIDA will guide you how to check your quality of your VHDL or Verilog code. Whether any flip flop is available, any latch is available, it will take the quality. Suppose latch is performed, latch is infer. Suppose you have written if and else. Suppose in this case, if clock is equal to 1, latch out equal to D. So in this way, it will perform your functionality, but it will infer the latch. In case of latch, we are not able to perform the timing analysis. In case of flip flop, we can perform all the timing analysis. So this will at the time of your VHDL coding, you are aware of it will this code will do the functionality of your functionality, but it is not possible to meet all the timing timing analysis or STA. So latch is not recommended for timing analysis. So before starting your synthesis at the time of RTL coding, all your synthesis and other goals are clear to you. Asynchronous feedback loop is detected. Suppose there are certain feedback paths, timing analysis is not possible for latches, timing analysis is not possible for asynchronous feedback loop. So this kind of information you will get at the start of the RTL. So you will have good quality RTL from scratch. So our aim is to generate RTL which can be easily processed by next synthesis and timing analysis tool. So once RTL is good quality, RTL is available, our next aim is to perform simulation. So purpose of simulation is to check the functionality, then functionality with timing. So at each level, function at RTL level, at post synthesis level, post layout level, we will do functional dynamic simulation with different inputs. At functional, we will do only perform only functionality. At post layout, we will check with interconnect RC parasitic also with the help of HDF file. So as you want to perform this simulation at different level at different options, you should write script and then do only simulation. In case of model sim, you can do files, or in case of VCS, you can make files. So here we can clean up every all your database and then start your compiling your RTL files. Then you can see in case of compiled DB, we are checking all the quality of check with respect to line coverage, condition coverage, FSM coverage, toggle coverage, branch coverage. So in next slide, I will show what this coverage will. Suppose this in linting, we have checked the quality of check, but in case of code coverage, we will check the quality of our test bench, whether whatever the functionality we are achieving. Before starting any simulation, we should aware of our test plan. So in test plan, we will define what is my input, what is output, whether all the conditions are met or not. So we have written in, suppose in this case, my score is only 74%. So in this case, line coverage is 63%, conditional coverage is 91%, toggle is 78%. So I should go to that particular warning and check whether all the outputs are toggle, or 78 is sufficient, whether all the functionality is met or not. In case of line, I have is only 63.25% line coverage I have achieved. So there are a lot of redundant lines. I should remove that line so that I will speed up my simulation. So this will take care of your goal is not to do simulation, but how efficiently you use your resources and perform your analysis. So with because manually you cannot quantify your functionality, but with the help of coverage analysis, the project leader can analyze the that means integrity of each block, and how this quality of block can be analyzed with the help of this coverage analysis. So after your RTL coding, quality of RTL simulation, the next step is the synthesis. So in synthesis, we can do convert this RTL to get level netlist with the help of technology specific library. Up to RTL, it is independent of technology. From RTL, technology specific .lib or liberty format will come into picture. The .lib contains the timing and power and noise library for particular technology. So we will convert from RTL to VHDL with the help of HDC constraint. So two inputs are required for synthesis. One is technology library provided by Foundry and HDC file provided by the user. So you should aware of what is its load. Suppose in this case, I will provide this set load 15. So in this case, I know my output load is 15 puff. Input delay, what is output delay? So all this input and environment, input delay, output load, output driving cell is to be provided by the designer. So for this purpose, designer should know its application environment. So according to this application, according to this HDC constraint, synthesis tool will optimize my design. So this is the schematic for the design. Then there is need for this scan synthesis, which will replace my normal flip-flop with the scan flip-flop, and all the nodes and are controllable and observable. So for that, I have to define DFT protocol: scan input, scan output, scan enable pin. In case of if you are using divided by two generated clocks, you have to insert some test mode. In this case, my processor clock is master clock and watch clock is divided by clock. So this clock is not controllable in case of DFT. So I have to add one mux and add one test clock for testing of that divided by two clock. So you should take care of the different clock domains at the time of design for testing. So then this synthesis tool will generate different reports. So we will go to next step is formal equivalence check. It will check the equivalence between the RTL and the post synthesis netlist. So for at each stage, post layout or post DFT, post clock tree synthesis, post layout, we have to do formal equivalence check with respect to RTL. The next step is floor planning and placement and routing. So our goal is to finalize the floor plan, finalize the number of IO pads, then floor plan the placement of macro. So this will take care in the case of layout. We have to calculate the number of IO required. What is the distance between this IO pads? What is the pitch allowed? What is the suppose this my package this die size is suppose 3 mm by 3 mm, and this complete package size is around 6 mm by 6 mm. So this small dice cannot be fit into bigger package size. So I should aware of the what is the availability of the package. So in that case, I have to increase my pitch, and I have to make my chip bigger so that it can fit 6 by 6 mm package. So I have to increase instead of though my optimized design is coming to 3 mm by 3 mm, I have to increase my chip size to 4 mm by 4 mm in order to fit that into some package available package of 6 mm by 6 mm. So before starting your this floor planning, you should aware of the external package environment so that you can decide the how many number of pads are required, what is the pitch between the two pads. Then next step is once floor plan is that means you have done floor planning over homework, then you should start placement. Then suppose this is the one example of placement. All the according to floor plan, I have placed all the IO pads. Then I have done initial floor planning. Then next step is to minimize the skew with the help of clock tree synthesis. Initially, I had done all the clock tree, assuming ideal clock tree network. But now here we will propagate all the clock tree with the help of clock tree synthesis. So this is one of the example of clock tree. Here we are inserted one H tree. So with the minimum skew of only 530 picosecond. So skew should be minimum. So we have inserted around 363 buffers, and all the flip flops are having equal. That means skew is very minimum. Next step is routing. So after placement routing, then I will insert this. This is the complete output of RTL to GDS2, and after this I will do post layout simulation. Then next final step is post layout simulation, when you have to do sign off with the help of prime time or any timing analysis tool. So in timing analysis tool, which will suppose will check all the timing for all the paths with the help of HDC constraint which are provided in the synthase. So this is the one of my example. In this case, slack is negative. So in the if in suppose timing is negative, then I have to again do some echo. That means echo and change, and then I have to insert some buffer and clear this violation. So timing analysis, if this is the final sign off, then I have to change my I have to run some echo analysis. I have to insert buffer or insert some delay cells, and I want to clear all the timing. And once this timing is clear, then I can go for the final sign off. In case of power, I have to do IR analysis also. So this is the complete RTL to GDS2 flow. At each level, we have to perform all the analysis with the help of design guidelines provided by Foundry. So you should follow all the guidelines provided by your design application, your design requirement, design environment. And if it is if you are following, there are 99% chances of silicon. That means first time success at silicon. So your goal is to not do only simulation, but simulation is just to perform check the performance of your check application only for functionality, but you should perform all the analysis at each stage for like only simulation, only RTL coding, only synthase or only place standard. You have to follow all these steps at each stage. All the all the physical verification, design rule checking, LVS, that should be performed according to your foundry specification. So this is the complete RTL to GDS2 solution. Normally we are using at SCL Semiconductor Laboratory, Mohali. So if any question, you can ask.